Beautiful to see you. It's a bit windy out here today, but oh my god, let me show you the garden. We start here, right here. I just saw this and I want to show you. Look, it's cherry blossom, it's cherry snow time, and there's even a blossom that's fallen down. And then you've got the lawn daisies, and it's just beautiful. So we're starting with the lawn and we're going up, and you can see the cineraria, but and the kowhai and the maple. But really, I just have to show you the cherry tree because it's fantastic. It's just beautiful, 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 beautiful. And I mean, it does this every year, but I never get tired of it. And I know that those of you who've been watching this for a little while with me over the years, you don't get tired of it either. What's to get tired of? It's just gorgeous out here. So here's the cherry tree, and hot on its heels, framed. I mean, look at this. These fabulous, just, you know, beautiful, beautiful, beautiful. And then there's the magnolia, which is just, let's get up close and you can see the flowers. And I love this camera. Oh my god, I bought the phone for the camera, right? It's a really nice phone, but the camera is just beautiful. And look, I don't think I've shown you the inside. There's the inside of the magnolia. It's just lovely out here. So we've got, you know, a madness of cinerarias. And I don't know how well the colour comes through. It looks alright to me, but I took a photograph of one of these and the colour came out completely wrong. So anyway, beautiful pinks here, and then there's a really, I think this all looks cineraria. And then these ones really are blue. So it's just wonderful. And there's a big space there where I dug something out. And, the ferns, I never get tired of the ferns. I just never get tired of this. And look, these are sprouting up. These are the rue plants, and otherwise known as Thalictrum. And this one has mauvey flowers, and this one, you can see it's got lighter foliage. Hi, Carla! It's got this lovely lime green foliage. The phone is a OnePlus. It's a OnePlus 12, and I really like it. I did some research when I was a new phone. And it's just lovely. I have not regretted taking the punt on something a bit different. It's beautiful. Look at the granny's bonnet. And this one, you know, it's this dusty purple. If I can just get you, there you are, focus now. Yeah, the connection is a little bit bumpy today, so hopefully we won't get kicked off. But I don't get tired of this ever. Look at this. Can we get some light on it? Just the cherry blossom is beautiful. Just love it out here. This is the time of year when everything is just fabulous. So have to celebrate the cherry tree. And I have to celebrate the new foliage on the roses. They're looking so healthy. I gave them some food. It makes a difference. And the wonderful fuchsias back there. You can see they've got some orange leaves on them. I actually need to prune them, I've realised, or they'll get leggy and long. But this is the spring garden. There's stuff growing in the ground. More cineraria. The very first rose is just looking lovely. And, this wonderful thing that I don't even know what its name is coming into flower. And, oh yeah, see the white one at the back? It opens out. It's got the most fabulous scent. And more cineraria. This bed's a bit messy, but see, it's got coriander in it. And so I come out here and pull some up and we eat it. And, you know, that's life of the garden. And the white Spanish iris, I'm really pleased to be able to show this off. It is a wonderful thing. I really like this. It's so elegant. So, I'm in raptures about my garden. But I've forgotten to tell you why I'm out here, right? Just waking up the Facebook Live. But I'm going to go inside now because I'm going to talk about God of Me. Because every Wednesday morning I carve out the morning and I spend it writing. And God of Me is this passion project, inspiration thing that kind of owns me. Let me shut the door, put the keys in their place. Get into the lounge where it's quiet. Kind of owns me, and it's this desire that I have to make information that has been really powerful for me, really transformational for me, available to the world in a format that, well, it's online, right? Because I sort of realised, excuse me, I'm just getting organised here. Right. I sort of realised that information is very readily available to people who are in any place where there's a decent internet connection, really. And if they have, they have a phone, obviously, or a computer, and they have a credit card or some way to buy stuff. You can get books, you can get information. Hi, Bev! All of that's there. But there are an awful lot of people around the world who don't have that. And it's a long story as to why that sort of came to my awareness, but I'm very aware of that. And I decided, this was my original inspiration, and it still really is my inspiration. I had this vision popped into my awareness of a group of young people, 3 or 4 of them, at the side of a dusty red road, probably in Africa somewhere. Hi, Alan! In my mind's eye, and they're just grouped around a phone because they've got a phone. If there's one people that have in the undeveloped countries, they have a phone. And I just thought, well, I want to put this into a format that is as light as WhatsApp and really easy for anybody who has a phone and an internet connection, because I can't control that. But if they've got that, I want them to be able to get this information. And I want them to be able to get it for free, because they can't pay for it, because not only do they not have a credit card, they don't have ID papers, they don't have a bank account, they don't have anything. So how in heck are they supposed to get information to empower themselves to change? Really? So that's where God of Me came from, and that was a couple or 3 years ago. I don't know when that thing first landed in me, but it stayed with me, and here I am doing it one Wednesday morning at a time. And so obviously it's going to be a website, and of course meanwhile, I work in IT, so I'm in the right industry to have skills and colleagues and people to ask and stuff. But right now, you can't have a website until you have content. So I'm writing the content, and you might think, what on earth am I doing talking about electrostatic energy, which is actually what makes your clothing stick to your body? If you try and take your clothing off, like if it's nylon or it's a synthetic, or it's a really dry day, and you try and take your clothing off and it sticks to you, and then you hear that sound as you take it off because there's little sparks. Or you even get a jolt, if you put your hand on a metal door. Or I used to go, like my supermarket years ago, there was a particular place where I would go and get a tin goods. And not every time, it was just, every second or third time that I went there and picked up a tin off the shelf, I'd get a jolt. I was like, I don't like this. But that is electrostatic energy, and I talked about it last week, and there's this big gap in my awareness and my understanding of what that actually is. So I looked it up, what is electrostatic energy? Well, electrostatic energy is the energy of a system of charged particles. And I'm thinking, well, that's really helpful. What the heck does that mean? So I started thinking, well, I need to answer these questions for myself, never mind you, or never mind anybody else who has never met this concept before. And you got to hope that they have had clothing stick to their skin, because that's the example I've used. If you're speaking to people who live in an undeveloped country, you cannot assume that they understand anything. They might have lived in the bush or in a mud hut for most of their life. So I have to use the most natural and generic examples that I can. A really good example of electrostatic energy discharging is lightning. Everybody knows what lightning looks like. Anyway, getting ahead of myself. So I started going into this, potential energy. It's the potential energy that's stored in this system of charged particles. Okay, what's potential energy? Well, if you have a ball and it's sitting at the top of the hill, it's got potential energy. If you let that ball go, the potential energy will be expressed as the movement of the ball going down the hill. When it gets to the bottom of the hill and it stops rolling, it's got no potential energy left. You have to pick it up and do something with it for it to have more potential energy, gravity. And of course, if the hill is only this high, well, it hasn't got much potential energy. If the hill's tall, it's got a lot of potential energy. So there's a distance factor in the potential energy, and that's actually important. But that was easy to explain. A system, we know, I mean, a system can be as simple as, I don't know, my hand and a glass of water. There's a hand, there's a glass, there's water, there's components, and they interact. And that's really all a system is, really fundamentally, because I looked up, what is a system? Well, it's things that work together to do something. And then, okay, the potential energy of a system of charged particles. Okay, how do I explain charged particles? What are charged particles? Huh? And so, we've talked a lot about atoms, and we've talked about protons, or we've talked about Planck spherical units. We've been going down the scaling factors to the most basic building block of matter, which, for the purposes of what we're talking about, is the Planck spherical unit. Actually, it gets smaller. It never stops. It's a fractal. It doesn't end. It gets bigger and it gets smaller, but it never stops. Okay? It's an infinity. But for the purposes of what we're doing, it's a Planck spherical unit is the smallest thing. But Plancks make up protons, and protons are most of matter, and protons are at the heart of every atom. So, an atom, and this is where I went, oh my God, I've screwed up. Because I suddenly was thinking, we talked about, well, basically I realized that when I was doing those calculations, talking about, okay, if a Planck is the size of Planck spherical unit is the size of a grain of sand, and then the proton is from here to Alpha Centauri, which is 4.12 light years or whatever it is. There's a huge scaling factor between them, right? And then I wanted to work out if that's the case, and that's information I got from physicist Nassim Haramein, and I know he's done his facts because he's a really cool guy who spent 30 years doing this, working this stuff out, and completely blown my mind with the information he's given me, which just clips into what I've learned from Dr. Joe Dispenza so well. It's like, wow. But I wanted to know if it's a grain of sand and then the proton is from here to Alpha Centauri. Oh my God, how big is the atom? And I was talking about hydrogen atoms, and my big oh my God was I realized that I was thinking wrong because I'd actually got hydrogen mixed up with helium. And I'm not going to go through all of that, but I did spend some time going back through the things that I've written. It's like, oh my God, this is so wrong. And I fixed it. I worked out how to do it without making it confusing. And then I redid the calculations. Because the first time I did the calculation, I knew it was pretty wrong, but I came out with the atom, by comparison to a proton being from here to Alpha Centauri, I came out with the atom being about eight times the size of the Milky Way. And that didn't actually strike me as terribly wrong, but I wasn't completely convinced. I went back and calculated it again, and I came out with about, halfway across the Milky Way. And oh, yeah, okay. But then I looked at it again, I thought, oh my God, I've done this thinking about a helium atom, and that's wrong because that's not the same size as a hydrogen atom. Went down the rabbit hole, fixed it up, and I now believe I've got it right, more or less. And so if the Planck spherical unit is the size of a grain of sand, and the proton by comparison is from here to Alpha Centauri, the size of the hydrogen atom, not helium atom, hydrogen atom, by comparison, is about 5.25 times as big as the Milky Way. That's just shocking to me. Hi, Jody! And I believe I've got it right this time. I'll probably check it again. But 5.5 times the Milky Way. And the thing is, okay, so grain of sand here to Alpha Centauri, 5 times the Milky Way. All of that is happening inside your hydrogen atom. One hydrogen atom in your body. The scales are just crazy. So I sorted that out. But I only realised that because I was asking the question about what's a charged particle and what the hell has this got to do with manifestation anyway, because that's really what it's all about, right? So anyway, having figured that out, I went back to this thing of charged particle. And so in an atom, except for a hydrogen atom, this is where I realised I'd gone off the rails, because a hydrogen atom has only got a proton in its nucleus. It's got no neutrons. If it gets a neutron, it becomes deuterium. I think I'd heard that, but I didn't realise. So a hydrogen atom, just a proton and an electron. It's virtually nothing, really. So anyway, a helium atom has 2 protons and 2 neutrons in its nucleus and a couple of electrons whizzing around. And so, yeah. So in that scenario, you can think about the nucleus. The protons have a positive charge. And you think they want to charge? What do you mean charge? Well, you know how you have a magnet and it's got two ends. And if you have two magnets, there's two ends that repel if you put them together, and if you flip one of them and put them together, it's going to stick. So the ones that stick together, one end is positively charged and one is negatively charged. And we know that opposites attract, right? So protons have a positive charge. Neutrons don't have a charge. They're called neutrons because they're neutral. The fun thing about neutrons is if they escape the nucleus, they immediately turn into a proton. So we think of them as, or I think of them as neutrons, as protons in disguise. So the positive charge is in the nucleus, and the electrons are a negative charge. They're whizzing around in a cloud around the nucleus, and the attraction between the positive nucleus and the negatively charged electrons is what holds the atoms together. And that's the same thing, I'm getting there, that makes your clothing stick to you on a dry day. How does that happen? So normally, in its ground state, I'm not going to say normal because I don't actually think ground state is that normal. In its ground state, an atom has a neutral charge. It's got the same amount of positive charge in the nucleus as it has negative charge whizzing around electrons. But what happens is that atoms share electrons, or they even lose them, or they gain them. They rip them off somebody else, and they do it making bonds. But also you get these loose atoms that have got an extra one or a short one, and if they've got an extra electron, they are negatively charged. If they've lost an electron, they're positively charged. Think about it. There's more positive charge in the nucleus and less whizzing around electrons. So, it's simple math. If it's lost an electron, it's positively charged. If it gains an electron, it's negatively charged. Now, when you're moving through the day and your clothing's rubbing against you, if some of the electrons that are on the atoms that make up your body get transferred to your clothing, or vice versa, electrostatic charge builds up between them. And you might think, but they're right next to each other. There is still a space between your clothing and your body. Because the news is, because everything is actually made of electrostatic charge, this is why this is so relevant, because everything that we think of as material is made of electrostatic charges. There's a lot of space, remember, between the tiny pieces of stuff that we call matter and the other tiny pieces of stuff that we call matter. There's so much space in between, there's almost nothing at all. That's where the electrostatic charge sits. So between your clothing and your body, there's a ton of room for electrostatic charge to exist, and it exists between the particles in the system. And they're close together, and you don't even notice it until you want to go and take your clothing off. And then it's all sticky, and it's like, oh yeah, I can feel that. And if you take the clothing off and you're in the dark, you see little flashes of light, or you hear crackles, or you may even get a little jolt, but it doesn't normally happen with clothing. The point is, that's the electrostatic charge discharging, is when you hear the pop, or you see the flash, or you touch the metal object and you get the jolt. It's built up there, it's sitting in a field. In the metal, it's sitting, I believe, inside in the space in between the atoms of the metal, because metal atoms have got lots of positive and negative charges in between them. I don't know enough. But, it becomes something that is discharged and it's no longer potential energy. It's electrical because it's moving. So, that is what happens. Things rub together with our clothing and we get an electrostatic charge. And when you make the gap wider, when you take your clothing off, you make the gap wider, just like the ball that's rolling down the bigger hill, it's got to go faster. It goes further. There comes a point where the electrostatic charge can't stay as a thing that's binding two things together. It's got to go one way or the other. So the gap gets bigger and it's got to jump. And that's when you have the experience of whatever you do. And it's the same thing when people, when you break the bonds between atoms, you're really breaking electrostatic energy. It's what holds things together. And the other thing is that in all the stuff that we think of as nothing, the space that I'm waving my hands around on and not even the air we're breathing, it's like the gap between everything. that's really full. It's so densely full of electrostatic energy. But it's disorganized. It's not made bonds. It's not settled into a pattern that's coherent enough to be matter. But that stuff is everything. And my point, finally, it responds to our thoughts and our feelings. And it's like, oh my God, is it really that profoundly simple? I'm not saying it's easy. Oh no, it's not easy. I'm just looking at the time here. But is it really? Is it that basic? And now I'm going to wrap it a bit because this is stuff that I've been learning. And I'm probably going to talk about this to my patrons on Patreon more. But just to put this in context of what I'm thinking. See, I'm aware that the reality, not what we perceive, not what we experience, the reality is that everything is, we're in this sea, this plasma that is made up of beyond counting, infinite amount of spinning vortices, tiny but very, very powerful spinning vortices of electrostatic energy. That's the field. That's the unified field. That's literally what it physically is. And it responds to thought. It responds to electromagnetism. And the brain is electric and the heart is magnetic. And you put those two together like Dr. Joe Dispenza teaches you, and you have impacts on the field. And even more than that, in my own model that is expanding, that I'm building on this basis, this beautiful model that Joe's taught me, that I'm learning from NASA more about the fundamental nature of reality and matter in the field, that it's this plasma. It's made of these tiny little spinning things. And I experience and believe, can't say I know because I haven't done enough study yet, but it is my observation and from what I've learned and listened and heard from him, from Nassim. And also because, I mean, where do I stop? Where do you stop? Where does anybody stop? We don't stop at our skin. We produce a field. And where does that field stop? Where does our resonance, where does the frequency and the vibration of me end? Well, for myself, I believe, experience that I'm fully entangled with the entire field, because every one of those protons in your body and in mine, every proton is made up of this enormous number of those little Planck spherical units. And those Planck spherical units, I've said they're spinning vortices, they're actually toroids, and they've got a tiny black hole in the middle. And those black holes are all connected with tiny Einstein-Rosen bridges, which are wormholes. And there is math that shows that the proton spins, the refresh rate of the universe is the time it takes for a proton to spin around. It's a immeasurably small amount of time. But, you might think, surely the universe communicates at light speed. That just wouldn't be fast enough. Think about it. Light takes too long to get from one side of the universe to other. It would all fall to pieces. There is a faster, like I said, you have the Planck spherical unit. There's something has to go through those teeny tiny wormholes. It has to be even smaller and faster than that. So there's this incredible thing that makes the whole universe communicate with itself once every Planck second, which is the spin of the proton. I might have that slightly wrong, but I know that it's however long it takes the proton to spin, tiny amount of time. The universe's refresh rate, like the refresh rate on your screen, but really, 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 really fast. And so that is how things can appear to happen instantaneously. They're not actually, but it's almost instantaneous because it's so fast. Every time the proton spins, boom, 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 it refreshes. And so with every spin of the proton, we have an opportunity to send a different message. And if you understand that every single tiny piece of matter in your body is networked with the entire universe, because it is, I mean, wow. Does anybody else here find that utterly mind-blowing? Wow. Because this is the truth. Because the mathematics, the physics that this guy has developed, and it's taken him 30 years to do it, shows that it's true. QED. There's so much more I have to learn and so much more to unpack for you. But this is why I'm excited about electrostatic charge. Because that's what everything's made of. And it's all spinning. And it's all networked. It's all connected. And we are intimately connected with all of it. And how we think and how we feel and how we show up every day has a big impact. And I am beyond curious. I'm kind of determined to work out how it works. Because I'm not the first person that said we must be able to do better, and I'm certainly not the last. And if other people on record, and many of them have done things that are so-called miracles, but they said they're just ordinary and you're going to do the same things as me and better, well then why not us? And maybe this is the means how it all works. It's all connected. And there's so much energy there. And we just have to work out how to tap into it. That's my interest. And I didn't know about any of this when I started working on God and me. But just imagine if all of us knew how to do this. We'd be able to look after ourselves and there wouldn't be any need for lack or conflict. So that's my passion. To work that out for me, to share the journey with you, and ultimately to have something useful to put on a website that people can benefit from, learn from, and become God of themselves. Because that's the only person we need to rule is ourselves. If we can rule ourselves, the whole world will be exactly as it needs to be. We won't need to rule anyone else. So thank you for joining in. Thank you for watching. I love sharing this stuff with you. If you're on YouTube, thank you for staying with me all this time while I rave. It's exciting. I love this stuff. I will be back next week again. If you'd like to check out what's on Patreon, please click the link. It's in the description. And I'll see you there. Big love. Until next week. Bye-bye.